So today we'll consider the series RL circuit. Okay. So after the completion of series RC circuit, today we'll consider the series RL circuit. So series RL circuit consists of a resistor and an inductor which are connected in series with a battery. So R stands for resistance, L stands for inductance. So resistance and an inductor is connected in series. So such circuit is called as series RL circuit. Okay. Then when battery is switched on in the series RL circuit, the current through the circuit takes time to become steady. So current through the circuit will not immediately rises. It will not become constant immediately. So, but instead of that, it will take certain time to become steady, to become constant. The reason behind this particular slow growth of current is that the electromagnetic induction. According to the Lentz's law, the direction of induced current in the inductor is opposite to the inducing current. When battery is switched on, the current will start to flow through the inductor, and inductor will produce the induced current that is opposite to the incoming current. So that current is due to the electromagnetic induction. We know that the inductor is a coil. So that coil will create the electromagnetic EMF. Okay. This opposition does not allow the current to become steady instantly, but current start to increase in the RL circuit slowly. So because of this electromagnetic induction phenomena observed in inductor, the current is opposed by the inductor. That's why the current through the circuit rises slowly. It will increase slowly. So that's why the transient phenomena, the variation of current is observed in series RL circuit. The reason behind the transient phenomena in the RL circuit is electromagnetic induction. So similarly, during the break of the circuit, suppose you switch off the battery, then also the current decreases slowly because of the opposing induced EMF. According to Lentz's law, the electromagnetic induction opposes both variation in current. Okay, whether the current is increasing or current is decreasing, the variation of current is opposed by the inductor. Because of that, during the switching off of the battery, also the transient phenomena is observed. The increase in current during the switching on of the battery is called as growth of current. Okay, we call it as growth of current. When you switch off the battery, the process is called as decay of current. Current decreases slowly. Current will not become zero immediately. Instead of that, current will decrease slowly. Okay, so that process is called as decay of current. Decay means decrease. So therefore, transient phenomena can be observed during closing and breaking of series RL circuit. In both cases, you can observe the variation of current. So that leads to the observation of transient phenomena. Okay. So today let us take the growth of current. When battery is switched on, how does the current increases in the series RL circuit we will consider. The considered circuit is consisting of a resistor of resistance R and an inductor of self-inductance L, which are connected to a battery of EMF E. So this is the simple circuit we are going to consider. So this circuit is consisting of a resistor of resistance R, an inductor of inductance L. Okay, so they are connected in series, and these two series combination, this series combination is connected to a battery through a switch. Through a switch. Okay. So that is how the circuit is connected, and current through the circuit grows slowly. When you close this switch, immediately the current start to increase, and that increase of current is opposed by this inductor L. Okay, and battery is having the EMF E, resistance of the resistor is R, and inductor is having the self-inductance L. We have to find what is the expression for this current. Okay, what is the expression for current? How does the current varies? That we have to study. Okay, at the instant the switch is closed. When switch is closed, the current flows through the series combination of R and L, and induced EMF develops in opposite direction. The inductor will oppose the incoming current and it will produce the opposite current. Okay, that will be the opposite to the current produced by the battery. It opposes the growth of current and allows the current to increase slowly. So this electromagnetic induction opposes the growth of current. That's why current will increase in the circuit slowly. Current will not become constant. Instead of that, the current increases slowly. So let us take I as an instantaneous current. Capital I is the instantaneous current through the circuit, and small e with the induced EMF, which depends on the rate of variation of current through it. So E is the electromagnetic EMF, or that is EMF induced due to the electromagnetic induction, that is directly proportional to di by dt. Okay, you know that the electromagnetic current or electromagnetic EMF is always directly proportional to the change in current observed in the circuit, or it is directly proportional to di by dt, and also it is minus di by dt, directly proportional to minus di by dt, because it opposes the current. Now let us apply the KVL and we'll solve the equation to find the expression for I. That is our aim. Okay. Now you apply the KVL to this circuit. At the instant the switch is closed. When switch is closed, the current through the circuit was zero. Initially, current was zero. When you switch on the source, when you close this switch, current start to increase from zero. Okay. Apply the KVL. The voltage across the battery is E. The voltage across the resistor is IR, current into resistance, and voltage across the inductor is minus L into di by dt. We know that. Okay, that is equal to 0. So each component you have to consider and apply the algebraic sum of EMF equal to 0. That is Kirchhoff's voltage law. So that equation gives you E minus IR minus L into di by dt is equal to 0, where this IR is the voltage across the resistor and minus dL by dt, L into di by dt is the voltage across the inductor, which is negative because of the fact that it is in the opposite direction of E. This IR is always negative. Already you know that. IR drop, it is called as IR drop. That's why the product IR is always represent the decrease in voltage. That's why minus sign applies to this IR also. Okay. So both are opposite to the direction of this battery voltage E. Now you solve this equation. This is a first order differential equation in I. di by dt is there. I is the variable and all other quantities are constants. Current is the variable because current is increasing slowly. That's why current is the variable with time. Time is the variable. Do the separation of variable and solve it by integrating this equation. This is a first order differential equation. We have to solve it. Solving, first you have to do the separation of variable. So therefore, you will get IR is equal to E minus L into di by dt. I will take this IR to the one side and you will get IR is equal to E minus L into di by dt. Therefore, I will be equal to, rearrangement you can do, I equal to E by R. So divide this equation throughout by R. You will get I is equal to E by R minus L by R into di by dt. Okay. Then you take this E by R to the left hand side or subtract E by R on both sides. You will get I minus E by R is equal to minus L divided by R into di by dt. Okay. So then separation of variable can be done easily. So just you make the cross multiplication, you will get the separation of variable. So this is the equation we have got in the previous slide. I minus E by R equal to minus L by R into di by dt. You take the terms containing I and di on one side. ಈ di ಮತ್ತೆ terms containing I ಅದನ್ನ one side ತಗೊಳ್ರಿ, dt and other constant on other side. So we'll get this particular equation. Okay, you will get di divided by I minus E by R is equal to minus R by L into dt. I will take this dt to the left hand side. So you will get R by L into dt with negative sign. Okay, so just you make the rearrangement of the equation, collect all the terms containing I on one side and collect the terms containing dt and other constants on the other side. So that does the separation of variable. Next step is to integrate this. Okay, integrate this equation, that will give you integration of di by I minus E by R is equal to minus R by L into dt, integration of R by L into dt. So this is of the form 1 by I minus E by R into di. So I is the variable which is in the denominator. It is of the form 1 by some I minus x. Okay, you have to integrate this with respect to I. That's why 1 by I integration is ln of I. So the result is ln of I minus E by R is equal to minus R by L. Integration of dt is t plus some integration constant c. Okay, so integration of 1 by I is ln of I. Ln means log to the base e. To find the integration constant c, what you can do, you can apply the initial condition. So when t is equal to 0, what was the value of current? So before closing the switch, current through the circuit was 0. Battery on agokinta munche current through the circuit was 0. That's why at t is equal to 0, I equal to 0. Put that condition. To determine c, put the initial condition, that is when t equal to 0, then I was 0. So t equal to 0 substitute madri, I equal to 0 substitute madri, you will get the value of c. Therefore you will get c is equal to ln of minus E by R. So you will get c is equal to ln of minus E by R. I is 0, that's why you will get ln of minus E by R. That is the value of c. Substitute here, you put the value of c in this equation, you will get, substituting, you will get ln of I minus E by R equal to minus R by L into t, plus in place of c we have ln of minus E by R. Then collect the terms containing logarithm on one side. Idanna ee kade tagolri, you will get ln of I minus E by R minus ln of minus E by R is equal to minus R by L into t. So collect the terms containing logarithm on one side. So this is of the form ln of m minus ln of n. So this is of the form ln of m minus ln of n, that will give you ln of m by n. Okay, already we know that log of m minus log of n is log of m by n. So you apply that logarithmic identity, you will get ln of I minus E by R divided by minus E by R is equal to minus R by L into t. So to solve this term in the bracket, you take R as a LCM here, R on a LCM tolri, you will get IR minus E whole divided by R divided by minus E by R. R gets cancelled. You will get a ln of IR minus E divided by minus E. Resistance R gets cancelled here. That is equal to minus R by L into t. Now this is the logarithmic equation. You express this logarithmic equation in terms of the exponential form. Already we have done while doing the derivation of charging of capacitor and discharging of capacitor, we have done that. So logarithmic equation can be converted into the exponential equation. So this is the equation we have got, logarithmic equation. Express this in terms of exponential form, that is IR minus E divided by minus E, that is equal to exponential to the power minus R by L into t. So successfully we have got an exponential equation. What is our aim? Our aim is to find out the expression for I. Expression for I namak beku. So collect all the terms to the other side. You take this minus E2 here. So you'll get IR minus E is equal to minus E into e to the power minus R by L into T. Take this E to the other side. You will get IR is equal to E minus E into T e to the power minus R by L into T. You can take E as a common factor. You will get I is equal to E by R into 1 minus e to the power minus R by L into T. So what is this E by R? This is voltage of the battery divided by resistance. V by R is nothing but maximum current. Okay. So this E by R represents maximum current I naught. Therefore, you will get the expression for I as I naught into 1 minus e to the power minus R by L into T, where I naught is called as E by R, which is the maximum steady current which flows through the circuit. The above equation gives the instantaneous current through the RL circuit. So observe here, the current is growing exponentially. As the T increases, this term in the bracket increases. So exponentially that term increases. Therefore, current will increase exponentially with time. Okay. So again, we can define the time constant of the circuit in this series RL circuit as we have done in series RC circuit. So let us do that. So this is the expression we have obtained for current through the circuit, that is I equal to I naught into 1 minus e to the power minus R by L into T. The growth of current is exponential. It shows that growth of current is exponential. This is how the current grows. At T is equal to L by R, suppose you put T is equal to L by R. During the time T is equal to L by R, what will happen? If you put a T is equal to L by R, this L and R gets cancelled. It will become e to the power minus 1. Okay. So the expression for current becomes I equal to I naught into 1 minus e to the power minus 1. When time equal to L divided by R. Numerically, it is L by R. Then the current I becomes equal to I naught into 1 minus e to the power minus 1. And that is equal to 0.63 times of I naught. So if you calculate 1 minus e to the power minus 1, you will get 0.63. Okay. This ratio L by R is called as time constant of the series RL circuit. Okay. So ratio of L to R, L divided by R is called as time constant of the series RL circuit. It decides how fast the current grows. Okay. The time constant, therefore, it is defined as the time during which the current rises to 0.63 times that of the final steady current through the circuit. So at this particular time, when time equal to L by R, the current through the circuit I becomes equal to 0.63 times of I naught, where I naught is the maximum steady current. Okay. So therefore, time constant of the circuit L by R is defined as this is the time at which the current through the circuit grows or rises to 0.63 times of the maximum steady current through the circuit. In the graph, you can observe this is the variation of current with the time. As the time increases, current increases and it will become steady after a certain time. That maximum current is I naught. When T is equal to L by R, it should be L by R, not R by L. It should be L divided by R. And so there is a typing mistake. So when T equal to L by R, the current becomes equal to 0.632 times of I naught. Okay. So each time only current to 0.632 times of I naught ಆಗಿರ್ತದೆ. And this particular time, that is L by R, is called as time constant of the RL circuit. Okay. So that is how we can define the time constant of the RL circuit. Therefore, the value of L by R decides the rate of growth of current in the circuit. So it basically decides how fast the current grows. If L by R is having the small value, the current grows immediately. So when this L by R will have small value when resistance is larger. When resistance is larger, L by R becomes smaller. So larger the resistance, faster will be the growth. Resistance bada ಜಾಸ್ತಿ ಇದೆ ಅಂತಂದ್ರೆ current will grow faster. Okay. Whereas when R is very small, then L by R will be large. Then it takes more time to observe the growth of the current. So current increases slowly. So value of the ratio L by R decides the rate of growth of current, or how fast the current increases in the circuit. That can be understood by knowing the ratio L by R. Okay. So that decay of current we'll consider in the next class.